Nassim Haramein from the Resonance Project returns to the program today to discuss his latest, to say the least, very interesting paper on the Schwarzschild proton. Nassim was first with us in 2008 and talked then about the holofractographic universe. Nassim has spent most of his life researching the fundamental geometry of hyperspace, studying a variety of fields from theoretical physics, cosmology, quantum mechanics, biology and chemistry, to anthropology and ancient civilizations. Combining this knowledge with a keen observation of the behavior of nature, he discovered a specific geometric array that he found to be fundamental to creation, and this laid the foundation for his unified field theory. This unification theory, known as the Haramein-Rocher metric, and his most recent paper, the Schwarzschild proton, lays the foundation of what could be a fundamental change in our current understanding of physics and consciousness. Stay with us for an exciting program. We are glad to once again say welcome to Nassim Haramein from the Resonance Project, who is joining us here today on the program to discuss the latest developments, the research, and primarily the latest research connected to the holofractographic universe model or theory, and of course the Schwarzschild proton paper that was released, I think, about almost a year ago. Now, this particular paper has gotten a lot of attention. It's gotten prizes from Belgium in terms of most important paper, and a lot more to discuss here together with Nassim. But welcome, Nassim, to the program. It's great to talk to you once again.
Oh, thank you. Thank you for having me again. It's great to connect with you guys.
Absolutely. Excellent to have you on the line. You're in Hawaii, obviously. A nice weather over there, we trust. It's a lot of snow here, obviously, but are you getting ready for the New Year's, Nassim?
Absolutely. We just celebrated the amazing solstice with the full eclipse of the moon. And, the weather here has been a little bit challenging as well. We had a lot of rain, and but now it's clearing up, and we're getting back to our good old Hawaii weather, which is fantastic most of the time.
Yeah, wow, that sounds nice. So
yes.
I guess, as I mentioned, the most important and I guess biggest development here since we last spoke back in 2008 must be your Schwarzschild proton paper. But I thought we could do this, if you're up for that, Nassim. Before we go into that in more detail and so forth, I wonder if you can give our listeners just a kind of a quick rundown, if that's possible, of the holofractographic universe model that you've been working on with the Resonance Project, Nassim.
Well, the idea is that the universe is a combination of finite boundaries and infinite curvature. That that you can describe boundaries like our universe, or a galaxy, or a quasar, or a star, or a planet, or an atom, or a subatomic particle, and a subatomic particle, and so on, towards infinity. And that we live in a infinite division of space universe, so that it has the qualities of a fractal structure, where in a fractal mathematical structure, you have this recurrent structure that continuously divide towards infinity, and it doesn't matter how much you zoom in, you still find structure, and you still find a division of the space. So the holofractographic universe is a universe where infinities are incorporated in our understanding of its dynamics and our understanding of its creative and self-organizing principles.
And what does that say more generally about some of the standards that we're working with today as the standard model of physics and so forth as well? Is this against this theory? Are they in collision, so to speak, with each other, Nassim?
A little bit, because a lot of impetus has been pushed forward in our current theories to find some fundamental particles, some particle at the base of creation that cannot be divided further, And, I believe that there's always further division possible. And that at the end of the day, when we get past, the nuclei of atoms, we're actually interacting with a field that has infinite potential in its structure, and that this field, is unknown to us right now. So, and although it's already present in the standard model, it's called vacuum fluctuation, or it's called 0-point energy, and it's or it's called Planck's density. So it has multiple names, but it all points to the same thing. And so this field of interaction that connects all things, this holographic field that connects all things, has not been understood. It was found, though, by the mainstream scientific theories almost 100 years ago, but it's been completely ignored, or very much ignored. It's resurfacing right now. But when it was found, it was so puzzling, it was so extraordinary, and it was so difficult to deal with in the context of the mainstream theories that it was basically put aside. It was relegated to the closet of skeleton of the mainstream scientific theories.
Yeah.
It was found that the vacuum itself, space itself, is fluctuating with almost infinite amount of energy. And, they just didn't know what to do with this. And instead of thinking maybe this is the fundamental energy from which everything emerges and return to, they just assumed that it was something that had no physical meaning, and they basically put it under the carpet for a very long time.
I mean, there's a number of mysteries surrounding our reality and what we know about the universe, but this is not in any way connected with the subjects of dark matter, or even the Higgs boson, or aka the God particle, or anything of that sort?
Absolutely, it's absolutely connected to all these things. It is, if this turns out to be correct, this field that I'm describing, this vacuum fluctuation, is the source of mass, which is what the Higgs boson, the Higgs mechanism is trying to explain. Because in current standard physics, there's not only no source for mass, there's no source for charge, there's no source for spin, and so on. And so actually, this field starts to explain all these things in much more simpler ways than the standard model does, and much more classical way than the standard model does. And what I mean by classical, like in a way that's much more understandable mechanically, that can be visualized, that has very fundamental geometry and so on, which the standard model does not. The standard quantum view basically is not anything you can visualize. It's very difficult to understand the fundamental mechanics of it. In general, they've abandoned the idea that real mechanics, real classical mechanics, are acting at the quantum level and so on, which I think, personally, is my opinion, is actually a cop-out that occurred almost 100 years ago. And this is why Einstein was really not keen on it. That's why Einstein really didn't like quantum theory, is because in one way they just said, we're just gonna ignore fundamental mechanics, and we're just gonna write math, and if the math comes out, then we must be on the right track. And then just went from there. And now the complexity is so incredible. When you look at string theory, you're dealing with 248 dimensions. They can be compactified in 10 to the 500 different solutions, and so on. Right. I mean, you're looking at incredible complexity. And I think whenever a model gets to that level, it's because something is fundamentally wrong.
It seems like it, and I want to get your take on the whole the CERN facility, the Large Hadron Collider. They've been trying to, and if any, how this connects with your work, or even maybe disqualifies the standard model of physics here, because they've been trying, as far as I know, to recreate basically a mini kind of Big Bang, and a while back they said this was successful, but they have had so many problems in getting this up and running, functioning correctly, and getting the results that they kind of want to. But what do you make of it, and do you think that they will be successful to achieve what they want to down there?
I think that they are gonna, one thing is that we've reached practical limits of how big of an accelerator we can build, how fast we can accelerate particles. So, in one way, this type of investigation is kind of a dead end, because if you built the largest, most powerful,
most expensive,
the most expensive, yeah, I mean, I think they're at $13 billion now.
Yeah.
Accelerator, I mean, and obviously they're having all sorts of technical difficulties because they're dealing with so much power and so much technology that inevitably things are going to go wrong, and so it's showing that we cannot build anything bigger. So now it's like, okay, well, does this gonna give us the ultimate response, the ultimate answer, and probably not. And so the idea that you can keep colliding atoms and getting smaller and smaller and smaller and smaller bits, and then writing math on it and exploring the universe that way is only valid if you could keep building larger and larger and larger accelerator and go faster and faster. But if you're being stopped at one point because you can't just keep building larger accelerator, then you're not going to find what you're needing to find. And so instead of looking for a fundamental particle, I think we should look for a fundamental pattern of division, a fundamental field of creation, and I think that's been missed. So now, in the context of their experiment, I think that it's still going to be very interesting and still going to be very valid. I mean, in one sense, already what they've found is supporting what I'm describing, and is not very supportive of their model. And so, for instance, what they did is they collided lead atoms at very high velocity, and they basically reproduced what the Brookhaven accelerator in New York had done, I think some 5 years ago, which I discussed in one of my physics papers, the physics papers I wrote on plasma. And when they did this, and you're correct, it's like a mini Big Bang, their result was something they didn't expect. What the result was, instead of finding what they were expecting, which they think of as a quarks gluon particle, they're trying to produce enough force to separate the gluon, which is the strong force, and isolate quarks, which are supposed to be particles that are smaller than the proton inside the proton. And when Brookhaven Laboratories tried to do that, the result was surprising. Instead, they got like a fluid, plasma fluid, which would not be expected by the standard model. The standard model would expect that they'd get a gas kind of structure with the quarks kind of isolated. They get this fluid kind of structure. And so the assumption with the Brookhaven Laboratory is that it wasn't strong enough to create that separation. And so they've doubled the strength of the collision, the energy of the collision with the Hadron Collider in Geneva, and they still got the same result. And it was just published recently. And I think in one of the articles, I think it was an article by National Geographic that was discussing this, the result was you know, I love this sentence in the article that says maybe we don't know everything we need to know, or we don't understand the strong force as well as we should. And that leads directly to that Swordchild paper.
That's right.
That I've published.
That's right. The strong force. It's a really interesting, take on this, and we'll try to break this down as well for those of our listeners out there who are not, physicists or mathematicians, obviously. But before we go and talk a little bit more about that, it feels to me also, just as you explained, that we have a field here of mainstream scientists who are trying to kind of limit reality to fit into a model when obviously we can't do that in one sense. But I don't know if you would, compare this whole CERN project to throwing down money down the drain in one way, but how would you do it if you had access to, let's say, a tenth of the budget that CERN has? What would you do, and how would you do it in order to try to explain the strong force and some of the mysteries that the scientists are struggling with, Nassim?
I would spend a lot of time elaborating the fundamental dynamics of that field that we call the vacuum fluctuation, to start to understand how the vacuum structure function. What is its dynamics? How does it produce mass and spin and charge and all this? And then derive experiments, which I've already done, devices that can reproduce the same dynamics in laboratory, and try to interact with that field, try to tap into that field, try to connect to that field, and prove its existence, and as well see if I can get work out of that field, see if I can get energy out of it, if I can get gravitational waves out of it. I mean, there's an amazing potential there, that's right there, just awaiting our awareness of it, awaiting our discovery of it, and it's been largely ignored. And there's many people, including Einstein, and other researchers that throughout the years, stochastic electromagnetic theories and so on have been derived, showing that actually looking at the universe from this vacuum energy field potential, when you write the math and everything, you can extrapolate, for instance, the black body radiation, you can extrapolate the Bohr atom, the hydrogen Bohr atom. I mean, you can get real results that matches, what we observe. And so to start to discover this, and the money, the expenses to do that research would be but a fraction,
right,
of what is being spent right now to try to isolate a Higgs boson.
That's right. And do you think that it's possible to tap into this, the vacuum energy, or this field that you're talking about, that without explosions, in a way, as they're trying to do, at CERN here, with accelerating particles together, and it's a kind of it's a somewhat violent and kind of brute, force way to go about this when I look at it. But what do you make of it, Nassim?
Yeah, I think it's very it's very typical of the way we've been doing science on this planet for a very long time. It's what I call the male approach to the universe. It's like colliding things, exploding things. Our idea of advanced space travel is to explode extremely volatile material,
Sure.
millions of pounds of extremely volatile material in a phallic symbol type of structure we call a rocket, just to go a few miles up, and all this whole approach has been very male approach, and yeah, the experiments that I'm discussing are much different. They're much more subtle. They're dealing with resonance field. They're dealing with curve. They're dealing with spin. They're much more female-like. They're much more of the female, subtle energy type of experiment that, you know, we call it subtle energy, but when actually you look at the mass and the energy potential of it, it's extremely large. But it's just subtle to us because we have been unaware of it. And actually that energy, just like the female, you know, component of our society, of our universe, is that actually the energy of birth, the energy that creates, you know, that generates, and that's been very much ignored.
That's right. And so let's get into the Schwarzschild proton paper a little bit, and maybe we can begin on the end of the strong force to connect it what we've been talking about here so far. And maybe you can tell us about what the strong force is for those of us who don't know. And is this the same energy, do you suspect, as the energy in this field or the quantum, you know, the fluctuation of the vacuum that you talked about?
Well, yes. You see, the strong force is a very interesting result of modern physics. I typically don't think of it as a fundamental force of creation, although in the standard model it is. You know, this what happened in very rough term is that almost 100 years ago, when we discovered that protons were in the nuclei of atoms, that the atom has a little teeny nuclei in the middle there, and it's got little particles in it that we call protons, and they're highly charged. They have a, you know, electrostatic charge, and it's a positive charge. That's why they're called protons. And you know, just like when you take two magnets and you bring them together, this is called the Coulomb force. And when you bring the two magnets together, they tend to want to repel if they are from the same charge.
Yeah, that's right. Yeah, that's correct.
And if they're really strong magnet and you push them together closer and closer, the strength of that force gets so high you can't get the magnet to touch, you know, if they're strong magnets.
Yeah.
And so it's a very strong force. Now, you know, when they found these little protons, highly charged, stuck in a very, very small radius in the middle of the atom, they said, oh my God, how come they're not being repelled from each other? You know, there must be an enormously strong force squishing them together into the nuclei of an atom. And since at the time, you have to put in the context of the time. At the time, the idea of black holes, I mean, Einstein had written his equations, and it did predict that, you know, singularities could exist, places where the gravitational field was so enormous that light would be absorbed from it, and so on.
Yeah.
But these things were very exotic, and everybody thought that they didn't exist for real. It was just a function of the math, and, you know, even Einstein thought we'll never find a black hole, you know, and so on. So in the context of the time, the idea that gravity, right, that the strength of gravity should be strong enough to squish these protons together was, you know, was shunned away. And the idea was that there must be some force that we don't know about. And, you know, they calculated how strong that force had to be.
Yeah.
And they just added it to the model. They just said, okay, this is the strength of what we're going to call the strong force. And they just threw it in quantum theory. And now the protons were squished or was held together by this force. But nowhere in their calculation did they explain where that force came from, how it was produced, what is the source of this energy that is holding the atom together. So it just became an open question. it was just assumed to be there. A little bit like electromagnetic fields, just like magnetism in quantum theory is just assumed to be there.
Yeah.
You know, they just say, oh, there's a, and you can imagine you're adding the strongest force in the universe in your model, and you're just not going to say where it came from. Well, to me, that is not an appropriate way to do physics.
That's right.
And so, and it will get you in trouble eventually. And so this is actually what the Schwarzschild proton paper is about. When I looked at it based on the holofractal graphic theory, when I looked at the atom and at the nuclei, I thought, well, you know, if it can be divided to infinity, since each division has mass, then the nuclei of an atom would have to be a little mini black hole, must be a little infinity there. And so I start to look at the proton as a mini black hole, and I start to make calculations. And lo and behold, when I calculated how strong the mass, how big the mass of a little proton black hole would have to be, it turns out that it's equal to the strong force plus the mass of the proton that we measure today. Meaning that the reason the mass they have for the proton is much lighter than the Schwarzschild proton mass is because they haven't added the energy necessary to produce a strong force. But if you actually account for it, right, all of a sudden it just adds up perfectly for the proton to be a mini black hole. And then if you calculate, you know, how that black hole would behave, like for instance, you know, what gravitational field it would produce. Well, you have all the gravity necessary to hold the protons together without the need for the strong force. And then if you calculate how fast they would spin around each other, you get exactly the speed of light, which is remarkable.
That is remarkable, you know? Yes.
A lot of the criticism I get, you know, doesn't pay much attention to like how beautiful it comes out. You know, so you get exactly the speed of light, which, you know, when you find some fundamental constant like that in your equation that comes out beautifully, you know you're onto something fundamental. And then, you know, if you calculate how fast, how many times it goes around each other in terms of hertz, you know, like two mini black hole protons spinning around each other, you get the typical decay gamma ray emission of the atom. You know, and then if you calculate what is the magnetic moment that you would get from such a system, you get very, very close to the measured magnetic moment, you know, of the atom in a completely classical way, in a very rough calculation that needs some help. But, you know, this was a first approximation. Yeah. And I think this is why when I presented this in Belgium at the University of Liège, in a physics conference, well, in a multidisciplinary conference that had a physics section, you know, that paper won the best paper award in that physics section is because it is so simple, it is so beautiful, and it comes out correct, although it predicts a mass that's much larger than the standard mass. But that's because, in my case, we're accounting for that force that the standard model just throws in as the strong force.
So this obviously is connected with, this is interesting because the mass, you're talking about the mass of a proton then is equal to, let's see here if I got this right. I try to understand all of this as well, and is equal to the mass, the total mass of the universe. Is that correct?
No. This is part of the calculation that I thought was very interesting, though, is that if you, so remember this vacuum fluctuation. So the paper says, okay, the reason the proton, the nuclei of an atom is a little black hole is because it's absorbing energy from this vacuum fluctuation field that's everywhere.
Yeah, okay.
And in that sense, the theory is very similar to another theory that Einstein actually worked on early on, called stochastic electromagnetics, where Einstein said maybe the atom is interacting with a field that we don't know about, and he assumed this field, this 0-point energy field, to be interacting with the atom. So I start a little bit like that, saying, okay, how dense is the field of the vacuum? How dense is the energy of space? We have calculated it in the standard model, and there's experiments that support that it really is there. And the calculation shows that that field of energy that we call space is actually dense with energy to the point that, when it's renormalized, when you put a cutoff, because otherwise it would be infinitely dense, it's 10 to the 93 grams per centimeter cube. And for the listeners, to understand what that means is that, that's 10 with 92 zeros following it. It's an extremely large number. That's the number of grams in a centimeter cube of space, the number of grams in terms of energy density. So if you took all the mass of the universe and all the stars in the universe, and you stuck it in a centimeter cube of space, that wouldn't be as dense as 10 to the 93. It would be 10 to the 55 grams per centimeter cube. You'd be missing 39 zeros on your numbers still. So you can imagine the vacuum density is extremely high. It's called Planck's density. And it's been supported in experiments, for instance, the Casimir experiment and so on, that shows that it's really there. So the paper says, okay, if this energy is really there, how much of that energy is contained, not in a centimeter cube of space, but inside a little bubble we call the proton? Like, if we think of the proton as a little sphere, how much of that energy, the 10 to the 93 grams, is still inside a teeny little proton, which is much, billions of times smaller than a centimeter cube. And when you make that calculation, it turns out that you get the exact mass of the universe, 10 to the 55th grams. And so in that Schwarzschild paper, I make the mention that this might be evidence that all protons are connected to all other protons through this field that we call the vacuum.
Yeah.
That all the information of all the other protons in the universe is present holographically inside one proton. And that may be why the universe is able to self-organize, because it knows where everything is.
So we have possibly an incredible amount of energy and mass contained in one proton. And we have a mini black hole in there, so to speak, in that sense. That's what it is.
Right.
In a way, it could be argued, or rather I want to ask you, does that to you mean that we have a multiverse, or are there little universes, if you will, inside of there? Or is the whole universe contained inside of every single little proton? I don't know if I've totally slaughtered the whole idea there, but is that what I can say, or can I assume good. That? Okay, go ahead.
Yeah, you can think of all the information of all other things in the universe is present,
right,
in each of the points, each of the proton, meaning that it's like a hologram, like a holographic plate. If you cut it in half, you still have all the information, and you cut it in half, and you keep cutting it, you still can have all the information in each of the bits of the hologram. It's a little bit like that. What I'm saying is that there's this field that we call space, that we call vacuum, that is full of energy, that's the carrier of all the information of all things. It's the thing that organizes everything, that produces the complexity we see everywhere, that produces the material world we see. I mean, it emerges from space and it returns to space. I mean, you know, instead of thinking of space as empty, we need to think of it as full.
Yeah.
We have evidence that it's full. It's in our theories, it's in our experiments, and so on. And so to start to realize this is actually the thing. The material world is just a very teeny weeny little portion of actually what's actually there, which is the energy of space, and that energy connects everything together. And that's why every proton has the information of all other protons in the universe. So every point knows exactly how to self-organize, because all the information is present in every point.
Back to dark matter again, then, in that sense, is this the mass that would explain how the scientists have inserted dark matter into the picture here? Because that's supposed to be, what is it now again, 98% of the mass of the universe, dark matter, right?
Yes, 96%, you know, and depending on the on the estimates.
Yeah.
But that's dark matter and dark energy. And those are put together. Dark matter and dark energy makes up 96% of the mass of the universe. So what happened again is this way of doing things that really, in some ways, quantum physics has allowed. It's like we can just throw things and just say we don't know the source of it. So this is what happened here too, is when we looked at the universe and the way it behaves, the universe not only expands, but it accelerates when it's expanding. We didn't have any way to make that happen in our standard model. Instead of, and then when we looked at galaxies and the way the galaxy behave, if we did an analysis with the standard gravitational theories we have today, all the matter in a galaxy should have flown out of the galaxy a long time ago. So in order for the model to work, we had to add an enormous, almost the equivalent of the mass we see in the galaxy. We had to add again that mass on top of it to make it have enough gravity to hold everything inside it. And we called that dark matter. We said it's mass that we don't see. It's some kind of matter that doesn't radiate, that doesn't interact with normal matter, and they just assume it was there. And then went on to try to detect it using, very expensive experiments again, and, and all this. And it's like, wait a minute, maybe we omitted something. Maybe this field, this vacuum fluctuation field, maybe this is the missing mass. And you're correct. You're exactly right. And actually, I'm just about to publish papers on this. The model of the Schwarzschild proton not only takes care of the dark matter, but takes care as well of the dark energy, which, is a big puzzle right now.
Very, very interesting. And the question obviously is, obviously it says a whole lot about reality and the universe. It gives us a lot already, what you have shared with us. But in one way, what more does it tell? I guess what I'm asking is, how can we use and utilize this knowledge, and how do we go forward? Or I'm asking in one way, have we just swapped one mystery for another here, if I put it that way?
Yeah, that's a very good question. I think it advances us a lot. One thing philosophically, the realization that there's this field all around us and inside of us that connects us all, it's actually a mathematical rendering or a physical understanding of the concept that we're all one, that, everything is connected, that we're unified through this field of interaction that connects all things. So that has a very profound meaning, because all of a sudden you start to realize that you're not isolated, that you are part of this amazing universe, that you are feeding information to this universe through all of the little protons you're made of. and that the universe is feeding you back information in terms of your reality. It's a feedback relationship with this field. And so right there, it has very deep meaning philosophically, spiritually, for society as a whole. I think right there it has incredible value.
Absolutely.
The other value is that the Schwarzschild proton paper very simply, very classically unifies the field. So we have this problem in physics where quantum theory doesn't agree with relativistic equation, and so we have forces like the strong force and the weak force that don't agree with gravity and electromagnetism, and we have not been able to unify them. Well, by looking at the approach of the Schwarzschild proton instead of string theory and its complexity, all of a sudden you unify the force in a very simple way, because you eliminate the strong force and you can eliminate the weak force as well. And so this is very, very powerful in terms of physics. And then, in terms of technology, if you realize that this energy is everywhere, that we are interacting with it constantly, that all the material world emerges from it and returns to it, and that it's incredibly dense in energy, that it's not trivial, it's very, very strong, then it becomes clear that if you understand how this energy functions, how it interacts with the material world, you can start to make devices to interact with it, and you can extract an enormous amount of energy from it. So then you realize we're not in a universe that is lacking in energy. We're not on a planet with not enough energy for everybody. There's infinite or close to infinite amount of energy, and we just have to learn how to interact with it.
Exactly, and that's the trick here. That's the most important thing of it all as well. Obviously, I mean, this is based on calculations, then, correct? Mathematics. You've come to this conclusion based on thinking about this, calculating it, so to speak. But could the theory that you put forth in your paper be confirmed with any kind of more practical experiment, or how could this be validated in any other kind of way, Nassim?
Absolutely. I mean, there is experiments that can be derived to not only confirm the theory, but start to learn how to extract energy or even gravitational effects from this field. And these technologies are not very difficult, or I should say, they may be difficult to built in a very they have to be very precise and everything, but in terms of their cost, they're fraction of a cost of the experiments that are being done in the mainstream today, and they could be done in very modest laboratory settings. However, it is extremely difficult, or it has been extremely difficult in the past to finance this type of research, because it's such outside the main impetus, the mainstream view, that it's extremely difficult for the financial world to have the vision to be able to, have the confidence to finance this type of research. But as well, I want to say that many researchers around the world have had results in extracting energy from that field in many different instances, and some of the experiments were mainstream experiments, like even the Z-pinch experiment showed, which is a hot fusion experiment that has been performed for many, many years, had some success, showing excess amount of heat, extracted from the experiment. There's the so-called cold fusion experiments that, that were supposedly debunked almost 20 years ago. Well, that's re-emerging. Many laboratories now are showing positive results and saying, no, it was very valid, and it had to be done right and all this stuff.
Nassim, do you think that that Fleischmann-Pons experimentation wasn't successful by certain scientists? Because again, if we're dealing in the world of quantum physics here, then your actually belief system is going to obviously contribute to the results of any kind of experiment. So do you think that could have been one of the problems with replicating that experiment?
Yeah, I mean, I think that's one of the problem. I don't see it in terms of quantum theory. I see it in terms of the reason why we have an influence on the material world is because we're embedded in this field as well, and we're influencing this field. And, you know, many psychic people and spiritual people and intuitive and sensitive people, you know, they talk about setting the space, you know,
sure.
And clearing the space and all this. I think what they're talking about is establishing a certain, you know, energy in the field, in that vacuum structure that allows for certain things to happen. So I think, you know, if the experimenter is trying to tap into that field, but his whole and his team levels of consciousness is that this is absolutely wrong, this is absolutely not going to work, then there's probably a good chance that won't. But even beyond that, when you look at what was done to those experiments at the time when Fleischmann made it public and so on, there was so many violation of protocols in many of the laboratories that had negative results and so on. I mean, you know, you got to realize that it was flying in the face of all of the standard model. It was flying in the face of all of the research that was being done in hot fusion. And, you know, research in hot fusion, you're talking technologies that are being built like tokamaks and deep devices that cost billions of dollars, millions and billions of dollars, and that employs hundreds, thousands of physicists and engineers and so on. And all of a sudden, some group comes out and with this little cell that's supposed to be doing fusion, you know, with a few watts of power, and an experiment that costs, you know, peanuts, and it's it was very threatening at the time. And so, you know, if you look at the whole history of it, you can start to understand why it was squashed and why it was, you know, put under the carpet for all this time. But it's re-emerging because the truth will prevail.
Sure.
And because humanity needs it at this time.
Well, exactly. That's an interesting take on it. I can't remember how long ago this was now. Was it back in the early 90s or was it 80s? Late 80s, I think it was.
Yes, I think it was late 80s.
89. Yeah. So is it, I mean, that's a strange question maybe to ask, but is it, are scientists more open-minded today than perhaps than then? And we've learned so much now, so much more, and it's a better time for whatever reason to reveal this information now at this stage?
Yeah, I think that, well, you know, you get all the students are growing up, and some of the old guys are, you know, retiring, and, you know, and as well, the environment today is much different, meaning, you know, today you have internet with information flying around the world every day, millions and millions of bits of information. And people, you know, are making experiments in their garage and talking about it on forums and all this, and you know, and so it's a completely different environment. And as well, today there's a very deep impetus to find new sources of energy. It's finally becoming more and more clear to people that we must transcend the oil paradigm, and we must find something better than solar and wind, and and so there's this push to find and so there's a re-examination of many things that happened throughout history that was basically put aside, and there was not so much impetus, there was not so much pressure to examine.
Sure.
So now there's more pressure to make that happen, including experiments that Tesla were doing,
Right.
and other physicists. So there's more and more of that coming out now.
That's right. The oil was chosen, if you will, by powerful men at that time, and now, of course, other people are beginning to look for other alternatives as well. So, Nassim, do you think that this primarily is about a different way of thinking as well, then? I mean, could someone, for instance, with your calculations and conclusions, somehow apply this to their own discipline, their own field, and maybe begin to develop it into I don't know, workable devices, or how do you see the next step in this process?
Absolutely. I think that you can definitely, if you can, the papers I've written so far are pretty rough because
Sure.
I'm working, on a shoestring. I'm a one-person band, and, usually these type of complex, I mean, certainly the papers I've written on Einstein field equation and plasma dynamics are complex paper. The Schwarzschild proton paper is a simple paper, and I wrote it in that fashion on purpose so that it could be easily understood by anybody, even with first year physics, or even a high school student can understand it, because it's pretty straightforward classical mechanics. But this if somebody actually takes these papers and actually look into it, and with the right attitude looks and read through the lines, and as well, look at the patent I've filed and so on, someone can actually start to understand where this leads, how the vacuum structure function, what we would want to do in an experiment to reproduce the same dynamics in the vacuum, and start moving in that direction. I think at the end of this road, we have literally technology that will provide energy for everyone,
Yeah.
in abundance, and literally star drives. I mean, we should be able to control gravity. We should be able to use gravity for propulsion without burning fuel. I think, understanding this fundamental field of creation that we are bathing in is the key to literally the ascension of human being on our planet. And it has very deep spiritual and philosophical meaning,
Yes.
and it has very, very deep technological meaning.
I mean, it's been asked before, and I think it's pertinent to ask again, and to people who are not, oriented around, power and huge amounts of just, grabbing, money and power and gain for that purpose. For them, it might be a kind of a no-brainer. Of course, humanity is ready for this, but from the other point of view, are we ready for this kind of access to that kind of power, Nassim, do you think? I mean, what will this do to warfare, weapons developments, and other kind of applications within that particular environment, if you know what I mean?
Yeah, I think that's a very good question, and I had to contemplate that for a very long time. Actually, a long time ago, almost 15 years ago or more, when I found many of this information from researching physics, but as well researching ancient civilization, I really had to ponder: do I really want to give this to humanity? Is humanity ready for this, and so on? And I think at the end of the day, that if you do an analysis of what has been happening on our planet that produces so much violence, and so much pain for so many different countries and individuals. I think that it all, if you kind of reduce it to one specific thing, I think it all comes down to a fear of not having enough.
Sure.
You know, not having enough land, not having enough power, not having enough energy. You know, much of the warfare that we have today on our planet is because of energy situations,
right.
and so on. So you can imagine that if all of a sudden our society discovered that there's almost infinite amount of energy anywhere they go, and they can have access to it. Imagine that our planet realized that by using this energy, they can produce gravitational drives that, you know, they can make vehicles and go and orbit Jupiter for the weekend.
Right. Yeah.
You know, all of a sudden the impetus to shoot at each other, the impetus to, you know, create misery, to fight for resources, you know, and all this, that pretty well goes away. I can see a society becoming peaceful because they realize not only they have infinite amount of energy, but as well they can access almost infinite amount of goods. I mean, if you can even just travel through the solar system, you know, there's all this material. I mean, if you want gold, if you want, you know, pretty well any material you want, including large amount of water, is available, for instance, in the tails of comets, or,
sure.
You know, huge chunks of ice are flying everywhere. I mean, so all of a sudden there is no need to fight for it. So I look at it in the other direction. I think that it's a positive step for humanity, and it's going to bring peace in our world.
So in a way, I mean, again, as you say, I agree with you there, Nassim. It's like it's all about resources and ultimately energy in that sense, because with energy, you could, you know, potentially, theoretically anyway, you know, do anything you want. Basically, if you have the right tools or development, you could replicate things, what have you. But what you're saying, I guess, is that you think that with power, that responsibility will come afterwards, if I put it that way. Because I would never want to give that kind of power to some of our, you know, so-called world leaders as it is today. I could see them want to tap the energy for themselves, if you know what I mean, and actually not give it freely to everybody on the whole planet. I understand, obviously, that this is a different approach, that this is about, I guess, you know, having it open source, if you will, in that sense, Nassim, and having it popping up on a scale which would be uncontrollable by those powers who would want to just benefit from this personally. But
well, you know,
what do you think
it has been. I'm sorry.
Oh.
It has been hugged by the powers that be for a long time. I mean,
Sure.
some of these developments have been there for a long time.
Yeah.
And it was disturbing to the status quo, and so they have been, you know, in many ways, you know, suppressed. But at this time in history, you have to realize that society as a whole is growing, and you know, in the earlier times, we probably weren't ready for this type of knowledge and technology. Now, I think it's a different world we live in. First of all, there's this community we call the internet that, you know, is moving information across the world, so it's popping out everywhere. It's not really controllable. It is the direction we are going to. The question is, can we do it on time? You know, there's a race against the clock. Will we go will we go in that direction, or will we self-destruct first?
Right.
And, you know, that is in the balance right now.
Sure.
And I'm very encouraged. I think we're going to make it.
Well, I think so as well. Otherwise, there wouldn't be any, you know, reason or to continue doing anything. Basically, you just lay down and give up. What's the point? So absolutely, I totally agree with you, Nassim, on that regard. We got to stay positive and do what we can, and encourage people to learn and to study these things for themselves. Obviously, because again, I mean, if this comes down to creative people basically applying different levels of knowledge to different fields. Anybody out there, so to speak, can be the next big inventor that actually comes up with an idea of how to successfully tap into this or utilize this in some way. So absolutely.
Yes, and like I said, I think that there's already many of these inventions that are around.
I think so too. Yeah.
Yeah, they have not been, brought forth and be successfully because of the mentality that's been prevalent. But that mentality is changing very rapidly because people are seeing the need at this point. They know, people forget that, like, even all these politicians and these all these agents and all these people out there, they all, or a large proportion of them have children. They do want to make sure their children have something left, that's
sure.
wonderful and beautiful and so on. And so, there is this push from humanity right now to transcend. And I think that push cannot be stopped.
Sounds good, Nassim. Let's begin just to wrap things up here for the first segment then, and just talk a little bit about your website as well. Obviously, you have the DVD Crossing the Event Horizon up there on the website. It's a 4-set DVD. And also we can talk a little bit about how people can get involved in different ways. The main website, of course, is theresonanceproject.org. You also have a member section set up there as well, Nassim. Tell us just briefly about that, will you?
Well, yeah, actually, we are a non-profit foundation because I believe that this research should be by the public and for the public. And so, by buying our DVD set and by becoming a member, you're actually helping finance this type of research directly, and you are participating in producing the new science for the new world. And that's, a lot of people ask, how can I help? Well, that's one very specific, very real way that you can help, like by becoming a member of the Resonance Project Foundation, buying our DVD sets. There's a new DVD that's coming out that's going to be published by Gaiam. Gaiam is a publisher of many, many different health DVD and so on. It's become a giant in publishing home video market and so on.
Right.
And so that will be coming out at the end of this winter. So, in the spring, early spring. And so look for it as well, and come and participate, come to my talks, or come and participate in our delegate program and emissary program. So the delegate program is a weekend course people can take and get deeper into the information. And the emissary program is a program where people can actually learn how to give talks and have the presentation and become what I call emissary of this information and help propagate it in the world and so on. So there's many ways people can participate and support.
Absolutely. Excellent, Nassim. TheResonanceProject.org.